Hi, welcome to ESI 412, Nanotechnology, Materials, Infrastructure, and Safety. I'm Professor Ukjun Nam at the Pennsylvania State University.
We're gonna talk about the signals coming from materials, and then we're gonna talk about the scanning electron microscopy, and then transmittance electron microscopy. So material signals. So in the early lectures, we talked about what is the major differences the nanotechnology in old times and the nanotechnology right now. The biggest differences are right now we can see those kind of nanoscale structures, and then we can understand those kind of compositions and then physical chemical properties of those kind of small nanoscale structures and the materials. So the one way to take a look at those kind of nanostructure is using this kind of electron microscopy. So this is the kind of characterization tool versus its kind of capability to observe these kind of structures. So this is optical microscope, which can roughly go down to the around 0.2 micrometer. And then this SPM, scanning probe microscope, we're gonna talk about that next lecture. Can see this kind of nano level, and then among this kind of SPM, those kind of scanning tunneling microscope even go down to the much smaller scale. And then this is scanning electron microscope. Actually, if we are using some special electron emitters, we call that as a field emission SEM, which can go down to the around 1 nanometer in resolution, and then the TEM can go much smaller in scale. So when primary electron beam hitting the surface of the materials, we can have this kind of signals from the material. So secondary electrons, OJ electrons, backscattered electron, and X-rays, and some cathodoluminescence. And then this is the typical interaction volume. So when the primary electron beam hits the surface of the material, in the very very shallow surface, which is on about 1 nanometer surface, we have an OJ electrons coming out, and then from surface to the little bit deeper, up to around the 50 nanometer, we have a secondary electron, and then a little bit deeper, we have a backscattered electron, and then we have a characteristic X-ray, and then some other X-rays coming out. So we do the same kind of power of the primary electron beam depends on the material. For the materials with the low atomic number, this kind of interaction volume is kind of much bigger, and then as the atomic number is kind of getting bigger, those kind of volume of the interaction is kind of smaller. And we do the same kind of so as we just increase the high electron beam of the primary electron beam, those kind of interaction volume is kind of getting bigger, but still depends on the materials. Those kind of interaction volumes are very different. So the secondary electrons, that electron is normally produced by this kind of inelastic interactions. So when those kind of primary electron coming down and then interact with some kind of valence electrons, those kind of interactions by the inelastic interactions, those kind of electrons at the valence band just coming out. And then since these electrons produced by the electron interactions, so we call that as a secondary electrons. But these electrons, its energy is kind of pretty low. So in most of the cases, the energy is lower than 50 electron volt. So the energy profile is something like this. So it is on about kind of lower than 50 electron volt. And then these electrons coming from the very shallow skin of that material, and then it is relatively independent from the atomic number, because those kind of interaction volume is kind of located in the very shallow skin. So that is why it does not affect by this kind of interaction volume. And backscattered electron is when those kind of primary electrons just interact with a nuclei, then it just happening elastic interaction. So in this case of that, those kind of primary electron does not lose too much energy, and then it just deflected and then just coming back. So in this case of that, this electron has very high energy. So in most of the cases, this kind of electron has more than 50% of its original energies. So compared to the secondary electron, this kind of a backscattered electron has a much higher energy. The OJ electron is when those kind of primary electrons interact with the electrons near the nuclei. So by that interactions, those kind of electrons ejected as secondary electrons, and then another electron to the located to the next shell, just coming down to fill that position. And in the case of that, when the other electrons in the same kind of energy level just emitted, if then in this case of that, we call that kind of electron as an OJ electron. And then instead of we are generating this OJ electron, when those kind of electrons just coming down to the lower energy levels, and then when it just emits X-ray instead of the emitting electron, we call this X-ray as a characteristic X-ray. So as to the OJ electrons, depends on the atomic numbers. Those kind of electron levels contribute is pretty different. So for the atomic numbers in the between 3 and 14, those kind of reaction is happening between the KLL, and then the other atomic layer has a different kind of energy level. And this is the way of those kind of producing characteristic X-ray and then OJ electron. So when those kind of X-ray is generated while these electrons moving toward to this empty spot, if that we call this an X-ray. And then when we making a backscattered electron, when the primary electron just interact with the nuclei, and then during that interactions, X-ray can be generated. So those kind of X-rays coming by the interaction between the primary electrons and the nuclei, we call that as a continuum X-ray emission. So we talked about all the signals we can get out of a material based on the primary electron application. So let's talk about the scanning electron microscope. So we talked about this kind of electron source at the when we talked about those kind of electron beam lithography. So basically this column for the E-beam lithography, and then this scanning electron microscope, the configuration of the column is kind of the same. So we have an electron emitter, and then we do have some optics to make this kind of electron beams much finer. And then in the last lenses are objective lenses and then objective apertures. And then we have the samples over here, and then depends on the detector, we can just make the images based on those kind of signals collected by the detector. So this is the example of the electron emitter. So this is the tungsten hairpin. So its shape looks like this. And then LAB6 is another kind of an emitter, and both tungsten and LAB6 just to generate some ionic electrons by hitting these sources by the electric field, electric current. And then for the field emission, we are using this kind of a very sharp tip. So we talked about those kind of a thermal field emission source and then cold field emission source. So this is the kind of same table that I showed you at the electron beam lithography. So this kind of a tungsten and then LAB6 using some ionic source is kind of a beam diameter is kind of pretty big compared to this kind of a field emission source. So in this case of that, we put very strong lenses just located in front of this kind of emission source. So we making this kind of a crossover to reduce the diameter, but because of those kind of Coulomb interactions among the electrons, it's kind of hard to reduce the diameters at the crossover. But still, its kind of a diameter is between 50 to 100K angstrom. And then when we moved to the Schottky field emission, this is in another word, thermal field emission source, and then cold emission source, this kind of a diameter of the electron beam is kind of pretty small. And then as to this kind of a thermal field emission source and then cold emission source, since this cold emission source is operated at the room temperature, so that is why this cold emission source need maintenance, which is on regeneration to remove the contaminant deposited on the tip in every 6 to 8 hours of the operation. But this thermal field emission source, its operation temperature is kind of pretty high, so that is why those kind of a contaminant coming out from the samples diffuse into the columns. It can deposit on the surface of the tip, but because of those kind of high temperature, those kind of a contaminant just immediately evaporated, so it does not need those kind of maintenance regeneration process. So when we have a specimen, and then when we have the primary electron beam hitting the samples, the secondary electron is one of the signals we will get out of the material. So the secondary electron detector, it has some kind of cages. So this kind of Faraday cage just apply the bias. So it just help those kind of secondary electrons just collected to the detector. So once those kind of electrons hitting this kind of a detector, it produce photocarriers, and then these kind of photocarriers multiplied, and then it just changes back to the electrical signals again. And then based on those kind of number of the electrons collected, we can just make the images. So in most of the cases, those kind of advanced FESEM, field emission SEM, it normally has two secondary electron detector, one positioned located in the inside of the column, and then the other one located outside of the column. So since we do have two secondary electron detector with the different kind of angles, like our eyes work, we can make in some kind of a 3D images. So this is the kind of image only use the secondary electron detector installed in the inside of the column. So it collects all the secondary electron just vertically coming to the column. So this kind of cavity structures, we can see the bottom of the cavities pretty well. This lower secondary electron detector, which is located the outside, so this one is a little bit angled from the substrate, so it has some kind of an angles to collect those kind of secondary electron. So that's why when we observe the same sample with the cavity, we cannot see the bottom of the cavities using this kind of outside secondary electron detector. So most of the SEM are just allowed to mix the signal from this detector and this detector, and then just mixing this signal with this signal. So at some ratio, you will have both advantages to seeing all the details of the bottom, and then some of the good contrast offered by the secondary electron detector located outside of the column. So when those kind of primary electron hit the surface, if your sample has this kind of very rough topography, depends on where you are observing, you will have some kind of an edge effect. So when you have some kind of samples like this, which has a bunch of nanowires kind of grown out of this kind of a circular nanoparticle, if then in most of the cases your nanowire is much brighter than these bulk nanoparticles, that is because when those kind of nanowire is something like this. So just considering all this kind of interaction volume, since this nanowire is kind of very extruded, something like this, so it can just generate much more numbers of the secondary electron. And then this kind of a flat surface, it has the kind of this much of the surface. So just compared with this case, the number of the secondary electron is much lower than this kind of a structure. So that is why this kind of a flat surface looks much darker than this kind of very sharp and extruded structures. So we call that as an edge effect. So another factors we can play with is an primary electron beam. So we can increase the electron beam energy from 0.1 kilovolt to the up to 30K. We can that is on high tension in another word. So what happened is as we use high electron beam, those kind of interaction volume is kind of much deeper, as I showed you in the previous slide. So we will have a much more secondary electrons generation. So it is kind of much better for kind of imaging those kind of small structures. So when you want to, so it's just the high electric field. It's just making not only producing more numbers of the secondary electron, but also it just reduce the diameter of those kind of electron beam when it just hit the substrate. So when you need to observe very small structures, those kind of high electric field of the electron beam provide much better resolution. But in this case of that, the secondary electron also coming out from the little bit deeper from the surface. So you started to lose some of the details from the surface. So this one is made out of the 20 kV, and this one is a 1 kV. So this one is a 20 times higher. So when you use a much lower high tension, you can see all the details of the surface. But when you increase the high tension 20 times, all those kind of details, all those kind of secondary electron signals coming out from a very shallow surface is buried by secondary electron coming out from much deeper. So that is why we lose those kind of details about those kind of surface. So that's the kind of a trade-off. So when people normally are talking about the resolution of the scanning electron microscope, people normally say the resolution at lower than 1 kV is something, and then 15 kV is something. So for example, one of the FESEM from the JAIS, which has offers its resolution is 1 nanometer at 15 kV of EHT, but 1.7 nanometer at 1 kV, something like this, because this kind of a lower high tension, those kind of a resolution is kind of much lower than this kind of a high tension. So backscattered electron detector depends on the type of the detectors. It has two sensors just made this kind of a circular shape, or it can use 4 different kind of detectors just configured something like this. So what happens is you can turn on this detector and then you can turn off this detector. So when you have this kind of a structure, you only collect the backscattered electron coming from this one, and then this side of the backscattered electron is not collected because you turned off this side of the detector. So it looks like there is some kind of a mountains, and then you are seeing the mountain only from this side. So using this kind of a way, you can observe the topography of those kind of sample pretty easily. And then if you have 4 detectors, you have more options to controlling those kind of detectors to observe those kind of topography of the samples. And this backscattered electron detector, it is coming out from the interactions with those kind of nuclei. So that is why it has some kind of a compositional information as well. So those kind of backscattered electron produced for the high atomic numbers of the materials, we can get much high intensity of the signals. So depends on the brightness, we can just tell the differences between the different kind of an element in the samples, and then this is the one of the example. So when we use the backscattered electron detector, this is the carbon nanotube, and then it has an iron catalyst. As we talked about VLS techniques to grow that carbon nanotube growth, we said those kind of carbon nanotube, we have a catalyst sitting on the substrate, and when those kind of source gases coming down, those kind of carbon nanotube grow something like this. So still, when those kind of catalysts are remaining at the end of the carbon nanotube, you can clearly have those kind of contrast using those kind of backscattered electron detector. And EDS, that's an energy dispersive X-ray spectroscopy. Using this way, we can identify the elemental analysis of your sample. So when X-ray hit those kind of detectors, it just generate those kind of carriers, and then it can just convert it to the electrical signals. So using this way, if one sample, this is the regular SEM images. So what we can do is, if we already knew about what kind of element made of these certain samples, if then we can search for those kind of specific element in this example, that is on sulfur and iron. But if you don't know about those kind of composition, you just roughly scanning your samples, and then you will identify what kind of element are present in the samples. And then based on that, you can just set up, I will put red color for the sulfur and then green color for iron. If then, after you just scanning it, you may just mapping it. So which area is kind of dominant by the sulfur, and then which area is kind of locally kind of rich, iron rich kind of an area. So this is a pretty powerful tools when you need to identify those kind of composition of the element on your sample. So as we discussed, those kind of secondary electron and then backscattered electron, which energy is kind of pretty different, and then this is on about 50 electron volt. So those kind of secondary electron has a pretty low energy, but this kind of backscattered electron has much higher energy, and then the OJ electron is located in between. So the secondary electron not only produced from your sample, but also when those kind of backscattered electron coming out, and then it just hit the lenses, it also produced from the lenses, and it can be produced everywhere. So this is the kind of a technology used for the advanced scanning electron microscope. So what happens is, when we apply this primary beam to the surface of the samples, we will get both backscattered electron and secondary electron. But those kind of advanced scanning electron microscope has both detectors located into the column, secondary electron detector and then backscattered electron detector. So the mechanism to filtering this kind of secondary electron is a little bit different, depends on the tool. But this example, people can apply a small electromagnetic field at the tip of the column, so it can just deflect those kind of secondary electron, and then it never be able to reach this kind of a detector, and then it only make those kind of a high energy backscattered electrons can make to the detector. So using that way, we can just filtering the signals based on the energy of those kind of a secondary electron. So when we use this kind of a secondary, this kind of a configuration of the detector, yeah, we can easily identify this kind of a different kind of an element of the materials. So using the secondary electron images, everywhere looks like pretty much the same. We have a little bit of the brightness changes, but when we just filtering out most of the secondary electrons, those kind of a contrast between among the materials are much better in contrast. So this is another example. So this is the kind of an example of the image using the secondary electron detector. So this shiny area, that is because when we cut these samples, this area is kind of making this kind of very sharp edges. So the reason for this kind of a bright image is more likely a edge effect. So using just a secondary electron detector, we cannot distinguish which structures made of what kind of an element. But if we are filtering those kind of a secondary electron, or if we are using just a pure backscattered electron detector, this image turning to something like this. So those kind of edge effect is kind of minimized, and then we can see all different kind of contrast, and then this kind of all different kind of contrast represent all different kind of material. So this is another kind of images when we use the this kind of a detector. So another way people are doing is, and we are talking about the technology, just to manipulating those kind of a small electromagnetic field generated at the tip of the cone. Another type of the similar kind of a function is some SEM can apply bias to the stages. So depends on the bias we are applying to the stages. If those kind of secondary electron has around 30 electron volt, and then if we bias about 10 electron volt, the secondary electrons which energy is lower than 10 electron volt never be able to escape from the samples because it was all trapped by the bias we applied to the substrate. So using this way, we can filtering the secondary electrons based on the energy it has. So using this way, we can just have a much clearer images. If then, why we wanted to remove this kind of secondary electrons? Actually, the secondary electrons is kind of pretty useful to making certain images. But the secondary electrons, since it has a very kind of a, its number is kind of pretty high at the low energies. So when we are working with an semiconductor or insulator material as a sample, those kind of secondary electrons not only contribute for an imaging of your sample, but also it contribute for a charging effect. So it just build up on the skin of your samples, insulator samples, and then it just locally build up the electric field. And then when the next primary electrons coming down, those kind of locally built electric field just deflect the beam, and then you cannot make the right shapes. And then instead of your just having this kind of steady state images, because of those kind of deflection of the electron beams, your images seems like keep flowing to one direction. So you can just have a good imagings. You don't have enough time to kind of use those kind of focus and then or stigmatization or those kind of things. So if you are remove those kind of secondary electrons somewhat, if then it is kind of much more advantageous when you are making some images out of this kind of, especially for the insulator. So this is the image of the photoresist. So when using those kind of filtering out low energy secondary electron beam, you will have much clearer images than without those things. So this is the same kind of technology to remove those kind of filtering secondary electrons. And then this slide is kind of pretty interesting. So it just shows the red circles coming out from all edge effect, and then this blue circle shows what the topography information, and then the yellow shows the charging effect. So when you are seeing here, these kind of edges are a little bit darker than the other area. So these are all coming from those kind of charging effect. So this slide showed which area has what kind of an effect. And then because those kind of high atomic number material produce much high signals of the backscattered electron, so when we detect the samples, which is a mixture of the two different kind of compound with a different kind of atomic number, we can clearly see this kind of a different kind of a brightness when we use the backscattered electron. And then the secondary electron detector does not offer that kind of a compositional information. And then this is again the secondary electron detector does not show any differences between the element, and then it even has this kind of a charging effect. But using the backscattered electrons, we can clearly see different kind of an element based on the different kind of structures, and it also does not have those kind of charging effect. So when we working with this kind of SEM, we might want to working with the magnification and then aperture alignment and then stigmation. So the magnification is basically the ratio of your scan area of your sample versus your screen. So if your screen, you know, the size of your kind of a screen in front of your SEM, so this area versus this area, the difference is directly the magnification. And why do we need to use very fine beam diameter? Each of this kind of magnification, we have pixels. We just have like your kind of a computer monitor, it has a certain numbers of the pixels, right? So at the low magnification, this area and then this area is almost getting closer. That means if you have a certain numbers of the pixels in your screen, as this area is kind of getting bigger and bigger, those kind of pixel size is relatively bigger than your electron beam size. So that is why in the low magnification, no matter what kind of an electron emitter you are using, you can have a relatively good images. But as we are going to the much higher in magnification, those kind of pixel size is getting smaller and smaller. And from that point, some of the electron emitters, like a tungsten, which beam size covers couple of the pixels. In this case of that, the signals is the sum of the all these kind of 6 or much bigger kind of pixels. So that is why those kind of images started to blur. So to get a best images, if we have a very small diameter of the beam, no matter how these pixels are getting smaller and smaller, still those kind of electron beam are just covering 1 pixels. So that is why we can just still have a very sharp images. Another thing is we have this kind of a configuration of the columns, and then we have lenses and apertures. If this kind of a beam axis is not aligned properly, if then, as we just are working with the focus, as we just as those kind of images kind of closer to the right focusing, if this kind of a shape is kind of a circular dot, instead of we are just seeing this kind of an edge of the dot is kind of getting clearer and then getting blurry, these images started to move around. So in the case of that, that's because of those kind of a primary electron beam axis is not well aligned. So in the case of that, we are using another kind of options like on wobbling. So this wobble is the machine just to keep changing its focus from under-focused and then over-focused. So using that way, when those kind of images under-focused and then over-focused, those kind of images moving X directions and then Y directions. So using those kind of XY apertures, we try to make those kind of movement of the images as small as possible. And at some point you are seeing the image seems like coming toward to yourself. In the case of that, we can say those kind of axis of the primary electron beam is kind of well aligned in the center. and we call that as an wobbling. And then using that way, we can align those kind of a primary beam on the right position. Stigmation is when we focus those kind of electron beams just finally, when it's just coming through the objective lenses, it's just demagnified like this. So when those kind of beams demagnified, if those kind of objective lens does not work perfectly, those kind of electron beam is not perfect circle, but it has a kind of an ellipse, this direction or this direction. So those kind of an ellipse shape of the primary electron beam make the final images much blur. So in the case of that, we control that stigmator and then just to make the primary electron beam to be much more perfect circle. So that is that application. So let's talk briefly about the TEM. So TEM its configuration is something like this. We have an electron source, and one of the biggest difference between TEM and SEM is we have the samples in the very last stages for the SEM, right? But TEM, we load our samples in the middle of the column. And another big difference is on SEM. For some SEM, we can just load 12-inch wafers. But TEM, it has a fixed size of the sample. So this is the kind of a typical kappa grid used for the TEM. So the diameter of the grid is always 3 millimeter. So after putting this grid into the holder, people just have this kind of a lock. So we can just tilt the samples and whatever we want to have. So we have this kind of a specialized kind of holders attached to the in the middle of the column. So in this case of that, those kind of primary electron beam should pass through the sample. That means the sample should be very thin. So it should be thinner than 100 nanometer, but it should be much thinner than 100 nanometer. So using the configuration of the different kind of lenses and then apertures, we can have a very different version of the images, which is a bright field and dark field. And then diffraction image is also possible. And then just mixing with this kind of diffraction images and then bright images, we can achieve high resolution TEM images. So this is the example of the bright field. So it looks like pretty close to the SEM images. So this is a silver nanowire, and this is the kind of a carbon tube. So when people want to observe this kind of a nanotube, what people are doing is those kind of a kappa grid like this. It has a very kind of a mesh structure like on carbon films, very thin carbon films coated on the kappa grid. So using the VLS technologies, we will have this kind of a nanowire growth on substrate. then using a kind of a razor blade, we just scratches this kind of a carbon nanotube and then harvest this kind of a carbon nanotube to a solution like an acetone. And then there are a bunch of the carbon nanotubes are kind of dispersed. Using this kind of a carbon nanotube inside of the square, which has a carbon film net. So as we just catch fishes using net, we just simply harvest this kind of a carbon nanotube or whatever nanotube through this kind of a carbon net. So in the case of that, this is the net, and then this is the nanowire. In this case of that is a silver nanowire. So using the bright field images, you can observe the shape and dimensions or things like that. Right now, its scale is on about 50 nanometer, about here to here. And then this is a 5 nanometer, about this much. So from this point, when you mix this kind of a diffraction images with the bright field images, you can see all this kind of a atomic arrangement. So this is a 2 nanometer, and then all this kind of a white dot represent each of the silicon atom. And when you grow some kind of a single crystalline or polycrystalline material, you can use different kind of options like diffraction images. If then you can identify those kind of atomic layers is which directions, aligned which directions. So for that, like this, we can just use this kind of lenses and then apertures. So we can just make the intermediate image plane. Instead of this kind of images, we can just make this kind of diffraction patterns can be shown, and then this kind of diffraction patterns just transferred to the image planes. So in this case of that, we can identify those kind of crystal direction of those kind of material. As to the SEM, those kind of high tension, electron high tension is on the maximum 30 kV. TEM, it can go up to 300 kV. So its high tension is on about 10 times higher. So even though those kind of a spot of the electron beam is kind of a much smaller than that of the SEM, it generates a very high signal of the X-ray. So we can also use EDS for the TEM. So using the EDS, we attach it to the TEM. We can also do the compositional analysis. If we put the WDS, this one is an kind of monitoring the wavelengths of the X-ray. We can have much more accurate analysis of those kind of compositions. So today we talked about material signals, and then scanning electron microscope, and then TEM. So using this kind of electron microscopy, we can easily observe the shape and size or topography of the samples, and we also can analyze those kind of chemical composition of the sample. So next lecture, we're gonna talking about scanning probe microscope. Okay, see you next time.